So, yeah, this evening or at this time, depending on where you are in the world, I'll be talking about R2 agents. So, yeah, this paper was released by Microsoft, I think a couple of weeks ago, and I skimmed through it. Then I just made the mental notes that, okay, this will be something interesting to talk about. So, yeah, I'll be sharing that today. So, the motivation for this paper, according to the author, is basically the recipe for training a reasoning agent is usually you have like a bunch of tool call, then it's trained in like a multi-turn setting, and by default you get this really long chain of thoughts where the model spends a lot of talking trying to solve whatever problem in a particular domain. And some problems arise with this setup. Mainly, it's expensive on compute. You have to spend a lot of compute to both calculate like the forward pass and the backward pass. Then you have problems with the infrastructure. If you're having like a lot of tool calls in across your RL training run, this could be like a lot of load on whatever setup you're using to train your machine. And because of the nature of reasoning tasks, you have a lot of variance in the response length that the agent or the model produces. And then this variance in the response length gives you a lot of idleness during your RL training. So, for example, if you have like a really long sequence and a really short sequence in the same batch, while this short sequence is still processing, while this long sequence rather is still like generating tokens, verifying from the environment, you would have a lot of GPU cores idle basically. So there's also another problems that arises with training agents, which is noise from the environment. So this will be the first thing I'm going to talk about. Um, but yeah, let's just dive deep into this. So this is basically like a snapshot of what training and agents looks like. So you have the rollouts, then initially you have the prompt, of course. Then the agent generates some chain of thoughts, issues a to call, then the to call is sent to the environment send the response, append it, then just continue this, you get your final answer. Now, where the noise comes in this setting is that imagine, for example, the model is solving some mathematical problem. Then the model like tries to verify, writes probably like a small Python function to verify something. If this Python function, let's say, contains some error, the model will spend a few turns trying to fix this error before it then resumes its normal trajectory of actually solving the mathematical problem. So the authors note that this sort of trying to fix some intermediate problem before resuming the main problem adds a lot of noise during the RL training. Because at the end of the day, the model still gets a positive reward for solving the problem. But there's no forcing function for all of this like intermediate errors that the model makes when solving the task basically. So the authors note that there are two solutions that have been explored in other like literature, stepwise reward. So basically, for every step along the reasoning chain, it seems to me in spirit like process reward. So basically, you are rewarding every intermediate steps or outcome reward, but you add like some penalty terms to the trajectory rollouts that the model produces. But the authors decide to not go with any, and then they introduced GRPO resample on correct, so GRPO ROC. So this is like the main algorithm introduced in the paper. And the main idea behind GRPO ROC is that you oversample, then you downsample. Like that's just like a brief overview of looking at it. You oversample, then you downsample, which I'm going to explain in the next slide. Yes. Oh, shoot. Okay. So I'm sorry about the formatting. But basically, what they described was in GRPO, usually you sample G responses per problems or G rollouts per problem. This is the group in GRPO. But what the authors came up with is, okay, let's sample two G responses. So twice the number of usual responses, split it into two groups, the positive set and the negative set. For the negative set, sample uniformly, sample half of the negative set just uniformly. Then for the positive sets, so they had this like two intermediate things you calculate. So you have this p error, which is just like a stepwise function, um, like taking into account how many two-call errors that this particular rollout has. So for some rollouts, you have the number of errors over the total number of two calls, capped by 0.5. Then you have P format. So this P format, according to the authors, was just to incentivize having only one answer tag. Because according to the authors, they made a note that there were some trajectories where the model has the response, then answer, then response, then answer again. So there are multiple answers in a single trajectory rollout. So that's why they had this format constraint. So you sample from the positive set, inversely proportional to this P total, which is just the sum of P error and P formats. So to just go over the whole thing again, you sample 2G, split it into positive sets, split it into negative sets. Again, just based off of the binary reward 0 or 1. From the negative set, sample uniformly half of it. For the positive set, you sample inversely proportional to P total, and P total is just taking into account the number of two calls and how much this trajectory follows the specific formats that you're trying to enforce, which in this case is you only have one answer tag. So also you're sampling half of the positive sets so that by the end of the day, you still have your G completions to train the model on. So this is what brought about the idea of you oversample, then you downsample. So
Can, before we go on,
yeah,
can I ask for just to make sure I understand? Um,
yeah,
for the P format, the number of tags you mentioned it was answer tags throughout the trajectory. Can you
yes.
clarify like what an answer throughout the trajectory means again? Sorry.
Okay, So I will still probably mention it slightly towards the end, but basically the prompt template was something like, okay, you have answer tag specifically. So and because they only trained on mathematical problems, so you only have like a single integer answer, then you include it in an answer tag. So and then you only have one of these throughout the trajectory. Does
Okay.
that make sense?
It that makes sense why you would want that.
Yes.
Why in the data do we have difference? Why do we have answer tags throughout?
Yes. So according to the authors, it was in like in the trajectory. I guess they did some earlier runs when in trajectory they saw a bunch of answer tag, and like ideally the answer tag is meant to represent the final answer for this trajectory.
Yeah.
So but then they were seeing like a bunch of answer tags.
Oh,
So
okay.
that's why they decided to add this format penalty.
Got it. Got it. Yeah. So it's like it's kind of we would kind of consider that to be like messy data, I guess, or
Exactly, something like this.
why not filter it out? Like why do this complicated downsampling instead of just filtering?
Right, right. To be honest, I'm not exactly sure, but
Mhm.
so my response to that is it is more of an artifact of the trajectory rather than the training data itself. So the
Okay.
data is just like some mathematical problem that, okay, solve this problem. Then it is during the trajectory rollouts that you have a bunch of like assume um thinking, then answer, then thinking, then answer, then thinking, then answer. Meanwhile, you could have a bunch of thinking, but you're meant to have just only one final answer in the trajectory.
Okay. Yeah. Got it. Okay. That makes sense. Thanks. Thank you so much.
Right. So please feel free to interrupt me if you've got any questions. So, but yeah, basically this is like basically the rundown of the GRPO ROC. So I made some notes. Oh, yeah, so and we go back to our formula for GRPO. Basically, the only difference between the original GRPO and this is that we are sampling 2G completions from the policy, then filtering this G from the so filtering G from the 2G sets. Then every other thing is literally the same as the original GRPO, probably except for the clipping epsilon term, decoupling the high and low term. I think which was introduced in the DAPO paper. But almost every other thing is the same as the GRPO, which guess anybody's familiar with. So yeah, basically
I have a question.
yeah, sure.
So what happened with this set of negative trajectories that we have sampled?
Right. So yeah. So for the set of negatives, they just use half of them in the final set of completions. So basically,
okay. So,
yeah.
the set of all in the next slide is the union of sampled negatives and sampled positives.
And sampled positives, exactly. Yes. I should have done better to indicate that. But yeah, basically, like the new batch of data, the new group that you're training on is just union of sampled positives and sampled negatives.
So basically, with this scheme, it's very much like GRPO, except we kind of upweight positive trajectories.
Exactly. So, and I actually have a slide here that exactly. So, like, basically, they are still preserving the failure mode, like all the different ways that the model can get zero reward because they're sampling uniformly from the negative cases, but from the positive cases, they basically want to only train the model on the trajectories where there was efficient tool use, where like the model made less errors when calling tools. So I guess this was what the authors are trying to reinforce with the ROC method specifically. So, and I was going to talk about this next. This graph is just basically showing the proportion of tool calls after GRCO, GRPO ROC algorithm and like the out of the box GRPO. And basically you would observe that the percentage of tool calls per trajectory was actually less with the ROC method compared to the out of the box GRPO. So yeah, so I made this point because this was a little confusing for me when I read the paper, but I clarified that. And the idea is basically that the sampling probability for the positive cases is decoupled from the final reward. Because this seemed to me in spirits like outcome reward with penalty. But then the thing to note here is that this the model is still only being trained on the binary 0 or 1 reward. So it is just the filtration mechanism we apply for the trajectories. That is the new thing, let's say. So yeah, I just thought this was like some important notes to make while I was reading the paper. Yeah, so that was the first part of the paper, the RL training algorithm. Then they had also like a very quite interesting recipe as well, which is they first performed SFT on non-reasoning data. So their justification for this was that observedly, most RL training papers that are published, they do SFT on reasoning chains, and they observe that the initial response length is always like super long, very verbose. So they decided, okay, let's do away with this. They SFT'd on like instruction following data, JSON formatting data, basic like code usage data. So, and that was what they started the RL training with. And as they actually observed, initial reasoning chains, and even on average, there'll be a plot towards the end of the presentation also where I share some plots from the paper. But like even initial reasoning chains were shorter, and obviously you'd have like slightly more efficient compute training because you're not having like a lot of you're not the if your response length is shorter on average, I mean it's less demand on compute basically. And the data for this run was on for these two problems. Initially, they had 100,000, but they filtered for questions with like labeled answers, and they were integers. Also, they also formatted out integer formats like what I wrote here. So with exponentials or with weird floating values, they filtered all of that. So it was just only integers answers, and they were left 42K. Then they also employed multi-stage RL. So 3 stages basically. Stage 1, was like 300 steps. So starting with the with the SFT model, you train the model with 8K context window limit, and they observed that on average, the number of tokens, basically the response length, grew to about 4,000 during the first stage. So after about 300 steps, they observed that the reward and the evaluation scores sort of plateaued. Then in stage 2, they increased the response length to 12K for another 85,000 steps. And then they observed that the average response length grew to about 6,000. Then for stage 3, they carried out offline like filtration. So basically, the idea here is that you have these 42K problems, then you take the recent snapshots from stage 2, run all of these 42K problems on the recent snapshots, generating 8 completions per problem. So if the model got the questions like in all its trajectories, you filter out the problem. So the new data set was basically problems where the model could solve like between 0 and 7 out of the time. So this left them with a data set of like about 17,000 data points. And this was what they used specifically for stage 3. So stage 3 was meant to be like difficulty mode, let's say. So as stage 3 was for another 125,000 steps. So, and again, you would observe the slight increase in reason length as well. So stage 1, the average was like 0 to 4K, then stage 2, 4K to 6K, then stage 3, 6K to 8K. And they also observed steady increase in evaluation scores across all of the steps, across all of the stages. Something interesting to note was, which I will probably talk about at the end as well, was that the authors mentioned that after about 125 steps in stage 3, they did not observe any more increase in evaluation scores. They did not observe any more, like basically it felt like as if the model capacity, like the model reasoning ceiling was reached, and they tried a bunch of tricks. They tried a bunch of approaches, increasing the context length, increasing the temperature, resetting the optimizers, and none of them seemed to work. So they had a very interesting conclusion, which I would probably talk about at the end as well. But yeah, so basically their training recipe was non-reason SFT, this data set of integer-only answers with multiple rounds of filtration, then multi-stage RL. So this was the training recipe. Then we moved to the RL infra. I sort of mentioned this at the beginning, but in more detailed, basically an RL training pipeline is you have your rollouts. Then because of the nature of multi-turn training, yes?
Kind of about the previous slide. So in the first part, you were talking about how the model is trained to use tools, and then it looks like they training the model to score well on math problems, on AIM.
Yes.
Specifically.
Yes.
So I'm just curious what kind of tools to use they.
Right. So according to the authors, the tools they allowed to use were Python tools. So SymPy, NumPy, and then like basic Python. That was the those were the tools in the SFT data that they carried out initial SFT on. So Python tools, NumPy, SymPy.
Right.
That was all.
Thank you.
Yeah. So basically code tools. So yeah, basically we're talking about the RL infra and the problem with multi-turn agentic training. So basically the problem is you have a lot of idle GPUs when doing agentic training. The nature of two cores, the nature of multi-turn, the nature of it being long rollouts. It gets to the point where some completion is still like generating trajectories, some completion has ended, but cores of the GPU are left empty, and this could add a lot of time to how much your total training takes. So what the authors came up with, actually, I think they came up with about 2 major things. The first thing is they sort of decoupled the environment from the RL training pipeline. So the execution of tools can run async to the RL training pipeline. And yeah, so basically this is what I mentioned. You decouple the code environment from the pipeline. They also had the capacity for like 45K concurrent tool calls during a batch. Then they had this neat thing. I think this is the part where I feel the least qualified to talk about. But basically, the high level idea is that you have a scheduler. So, and as far as I understood the scheduler, it's monitoring the GPU KV cache during the training run, during the RL training. And once some particular task is completed, a new task is assigned. So the part where I'm not sure is how this fits into the batch size, and if this means the batch size is changing during the training. I'm not entirely sure, but like basically this was the high level idea, basically, that okay, you have the scheduler, and the idea is basically that everything runs async, so you can allow some completion to keep generating while some completion has finished, and then almost immediately it is replaced by a new set of prompts to be completed as well. So yeah, this is the RL training infra. Then, so yeah, there are these charts from the paper that looks like yeah. So there are these charts from the paper that looks like you're having a bunch of idle terms in the rollouts, and with more efficient environment service, you're able to make everything as compact as possible and evenly distribute loads among all of the GPUs. Then also, I already mentioned earlier, but they had 45K concurrent calls, at least the code environments that they built was able to support 45,000 concurrent two calls. And they also had latency of just about 0.3 seconds. So which I thought was, I mean, pretty quick. So yeah, experiment setup. The model that they used was Qwen 314B base and Qwen 2.5 b base. Because this was already an instruct model, they didn't perform non-reason SFT on this, and even actually throughout the paper, they only referenced this Qwen 2.5 b base a few times. So we're focusing on Qwen 314B base. So again, non-reasoning SFT, just for 3 epochs. For the RL training stage, stage 1 and stage 2, they had the sampling temperature of 1. Then stage 3, they increased sampling temperature to 1.5. All of the training was 510 steps carried out on 64 GPUs in about a week. So, and some of the results. So they were able to rival some of the top models on like popular maths benchmarks. So Maths 500, AME 24, AME 25, and Harvard Maths Tournaments competition. So you would observe that the agents here scored better than DeepSeek R1, Claude, or Opus. I mean, models that are like probably now not at the frontier of reasoning, but at least compared to comparing 14B to DeepSeek R1, it's the distance gap is quite a lot. Then across other benchmarks, even though the model was trained only on trained to solve mostly mathematical problems, they were also able to evaluate the final model across different benchmarks, so scientific reasoning, agentic tool use, general use, and the results also were pretty impressive. It is important to note here as well that after the non-reason SFT, they already got significant boosts in performance. So this is what is highlighted in this gray here. For example, the authors note that for this particular benchmark, BFCL, the base model got 0 on the benchmark, but then after the non-reason SFT, performance jumps to about 63, and then obviously slightly degrades after the three stages of RL training. But still, they were just trying to highlight the potential of the whole setup, basically. So another thing that the authors emphasized in the paper was the difference in the response length. Again, I said earlier that one of the problems with multi-turn agentic training is the fact that you could very easily have long chains of thoughts. So because of the non-reason SFT, and then the resample on correct, which is only mostly taking into account positive responses with, on average, shorter token sequence length. During evaluation, the average token length was actually comparably less than other models of around the same size, and even some bigger models. So compared to the base model, 2314B, the response rate is significantly different compared to the Coin 32B and this district R10 as well. You'd observe like the difference in sequence length is a lot. So they were just basically trying to emphasize the point that they were able to get reasonably decent performance for not a lot of tokens compared to other frontier reasoning models. And again, based on the way I interpreted the paper, this was due to, number one, the non-reasoning SFT, which kept initial response length short, and the sample incorrect, where the positive responses that are reinforced are those ones that, on average, they have shorter lengths because, on average, they make fewer mistakes. So, yeah. So they had ablations where they compared GRPO ROC to other variants of GRPO, other variants of RL training. And again, they had like the sense benchmarks results, specifically on AMI24. So the performance jump in AMI24 seems to me larger than at least Math 500 and AMI25, for example. And well, save for V2, it had like the smallest number of RL training steps. So their training run was more efficient than other training runs reported by other papers. So another ablation they carried out was comparing GRPO itself to other just GRPO with two call, but using the same model. So they still stuck with Quen 314B base, or Quen 314B now, the SFT version, and they carried out just GRPO with tools. So you would observe the AB24, AB25 scores, and then the average response length during evaluation across all of the steps. So basically trying to highlight the fact that GRPO resample on correct by itself leads to some performance gains. So yeah, this was what I said I was going to get back to this pretty much later. But the authors observed that the arrow training peaked after about 510 steps in total. And again, they tried a bunch of things to fix this. For some of the things they tried, they actually noticed that the model got worse as the training progressed. So worse evaluation scores, worse, let's say, cumulative reward across batch as the training progressed. And one of the conclusions they came to was that, okay, their current RL training, so resample on correct, as well as the entire pipeline, would not advance the capabilities of the model more than what had been done during pre-training. So it seemed to me in spirit that they were sort of alluding to the illusion of thinking paper, where yeah, basically that was my interpretation of the way they worded it. And the author suggested that a possible research direction could be, okay, with minimal compute, how can we reach the ceiling? So like if there is a ceiling already, if there's a ceiling already baked in during pre-training, then with minimal compute, can we reach the ceiling as fast as possible instead of like spending a lot of training steps, a lot of compute for like just marginal gains. So yeah, I guess yeah, that's all. Thank you very much for listening. If you've got any questions or notes you'd like to make.
Yeah, great talk, man. Thanks for bringing this in. I guess I was curious. Um, so their focus was kind of on minimizing the training costs. And they
Yes.
had a little bit of focus on minimizing inference costs as well, right? Because they had their
Yeah.
3 steps where they were trying to train a little. They were trying to generate a data set that was like shorter steps in general.
On average, yes. Yes.
Okay, but that was the only thing that they did to kind of minimize the number of inference steps, right? There wasn't anything else.
No, as far as I know, no, doesn't anything else. Yeah. But for the training steps too, they noted that or they had the notes that the non-reason SFT also like allowed the initial response length to be short. So this might have contributed to the shorter token sequence during training.
Got it. Yeah, I mean, I guess the thing that I'm a little bit confused about is that the paper seems to go in a couple of different, like, very different directions. Like they have their training
Yes.
emphasis, they have their
Yes.
inference emphasis, and then they also have this like
Yes.
engineering, how do we
Yes. Yes.
schedule the compute,
Yes.
like balancing
Yes.
emphasis.
Yes. Those are actually the three main, like the three broad topics in paper, the RL algorithm itself, the training
Mm,
recipe with the data, the non-SFT, non-reason SFT, and then the infrastructure side of things. So they had
mm.
those like three directions that they explored. I think was like each per section in the paper.
Got it. Got it. Did they
Yeah.
conclude? Do they have any conclusions about which was kind of the most impactful direction, or was it that all 3 together?
Yeah, funny enough, I was thinking about that. So they did not have any conclusions. The only thing I saw, which I already like noted, I guess, was the GRPO ROC, the RL algorithm itself. So
Mm.
but for the other things, like they just sort of said it offhanded that okay, yeah, with the infrastructure, they were able to get like super low latency for 45K concurrent through call requests. So, but comparing like apples to apples for each of the three, they didn't make the notes.
Yeah, I suppose the infrastructure could be just generally helpful for all tool use agents to have better scheduling for during training
Right,
processes. So maybe
right,
that's just obvious that that's going to help everything.
right. But also actually on the infra side, they did note that like they started off with Veru library, VERL. So
Uh-huh.
that's the library they started training with. And it
Mhm.
was with the very library that they discovered like a lot of the discrepancies with idleness and like a lot of load on their cluster. So then this, or at least their proposed infra was like an improvement on top of VRL library.
Cool.
Yeah, yeah,
Cool. Yeah. Thanks. Thanks. That's it for my questions for now.
yeah.
Um, yeah, I have a question. It's an agent.
Right,
Yeah, our star agent. I was wondering, and it uses Quinn, which is Quinn 3, I think, is the base,
right,
which
right,
is a decent coding model.
right.
Would it make sense to have a planning model and then call an
Hmm.
agent and just train the agent for tool use and then return the answer?
Right, right. So just before this presentation, like few minutes before, I was reading somebody from OpenAI wrote like a Twitter thread or an X thread on their performance at the ICPC competition, and they had so like the base result was GPT-5, but then they had like a small, a tiny subset of the thread where they noted that they had like another model that was actually doing the selection of results and like drawing up the plan for the problem, then selecting the final results when GPT-5 solves it. So I'm guessing that's sort of what you're like referring to.
Well, in this training platform, they're training it to
Hmm.
plan and they're training it to do tool calls. And they see, yeah, a 10% increase in
Right.
we'll call it errors.
I would just jump in and
Like,
say, like, I think planning and executing and separating those two functions. There's a ton of papers that have explored this for many years now. Like plan and write is one. Plan and act is another one that came out. So separating these two functions I don't think it just came up with that OpenAI blog post. There's been a
yes,
there's
yes,
been a
yes,
lot.
yes.
Oh yeah, yeah.
So like my point for clarification was,
Oh,
it seems to me that the planning, then execution would be more useful in like an inference time paradigm as opposed to like the actual RL training. So that's what I was asking, like, is it related to the OpenAI setup? So like, or let me say to be more specific, are you referring to planning an agent during the training itself or during like the inference test time actual deployment setup?
Well, I guess it would be inference, yeah, setting this up.
Yeah,
For
yeah. So
time.
for inference, I would I mean, it would make sense to me why that'll be useful. Well, I've not seen a lot of papers with like planning then with planning and execution during the training. So, but with inference, the common consensus seems to be just having a planner. Like you get some significant boosts in results.
And
Yeah.
yeah, with respect to that, they used Quinn. Did they try different agents that had different capabilities for tool use baked out of the base model?
Right. So they did not report this, but also another thing I wanted to note was that the starting model was when so it was like the base model that had not been instruction fine-tuned yet. So yeah, so the base model obviously it had gone through the pre-training stage, but there was no like tool use fine-tuning yet. There was no sort of instruction following fine-tuning yet. So they carried out the non-reason SFT with the like tool use, then JSON formatting, instruction following, every other like capabilities they were trying to elicit. I don't know if I answered the question specifically.
Yeah, I was just wondering if they made a note.
Right. No, they did not. The only model that they compared with was, which I mentioned, was Qwen 2.5 32B instruct. And even for this, they did not like extensively talk about it during the report. So it was just like an offhanded comment.
Because that would limit the number of
Yeah.
errors and then the number of tokens in the reasoning steps.
Yeah, agreed. Agreed. Dimitri, do you have any comments?
Yeah, I have a question. Curious if they, how did they incentivize the model to do a multi-turn tool use in the first place, or did the model just learn it on its own through the GRPL process?
Right. So thinking about it now, I should have included this in the presentation. But basically, in the prompt templates, it is like written that, okay, you have access to these tools. You can test your hypothesis. You can try to verify some things, and then finally put your final answer in answer tag, which they then verify. So my response to that is it was an artifact of the prompt versus probably JP just discovering it itself. So and as far as I know, there are some in-context examples for tool use. So and the model was able to again see examples of like how to call the tools, what the correct format is, what were the tools available. So yeah.
Got it. Thank you.
Yeah.
They used 0.5. If you go back a few slides to
Right.
the errors in the training procedure.
What slide specifically?
Yeah, right here.
Okay.
For the positive set. So 0.5, if no tool calls,
Yes.
then did they play with these parameters at all? Because
I was wondering that
it
too.
seems very small.
Yeah. Yeah. I mean, it's not like they didn't give any empirical reason for why they use 0.5 or even 1 here. They didn't give any empirical reason. The only thing that was mentioned was that with like if P total is large, then you can expect that either the model has like a bunch of two-call errors, or there are a lot of answer tags in the trajectory. So, but for any reasons related to 0.5 or 1 here, they didn't give any such reasons. In my opinion, this could as well have been 1 or 0.5 0.5. Yeah, no, they didn't say.
Yeah, just thinking out loud, but yeah, a higher number there would be better if a higher number there would mean it would encourage no tool use, right? It would encourage just the
So,
answer, and the lower number would encourage tool use.
No. Yeah.
The p total is in a denominator, so like the higher. So basically, like this p total is my understanding is that p total is p total error.
Exactly. So like an higher number for p total would mean that it would be like it has less probability of being sampled for the positive set. So which would actually mean that for example, you're having maybe a lot of tool errors in this particular trajectory, or there was like a bunch of answer tags, unnecessary answer tags in the trajectory. So like more p total, but
All right. So it seems to want to encourage tool use. At 0.5, let's just say no tool.
Okay. So you mean for 0.5 specifically?
Mm-hmm.
Yes. Actually, yeah, you're right with that. So if so the model is incentivized to use tools at least once. So if you don't use any tools at all, you still get the 0.5 error. So yeah, I get what you're saying now. So the model is incentivized to use tools at least once for the reasoning trajectory. Yeah.
Yeah, good.
I don't have any more questions.
Yeah, maybe on how it generalized.
Mm-hmm.
It showed data for different data sets. Were those
Yes.
what tools was it given in that case? Was it using Python again
Yeah.
for those data sets?
Yes, exactly. So it was still the same data sets, the same set of tools it had access to during training, it had access to during inference. But then again, it's hard to say how much of a use the tools would have been in the context of science reasoning. I mean, not every science reasoning problem are like mathematical problems. Some are like related to physics, maths, chemistry, computer science, different aspects. So yeah, I'm not exactly sure how useful the tools would have been on some of these benchmarks. But yeah, basically they had access to the same tools during inference as during the training step.
Okay.
Yeah.
Would it be better? What would happen if they added tools or swapped two tools?
Yeah. So my immediate answer for that is that for some benchmarks, I think you can expect that so for example, my thinking would be benchmarks like science reasoning, where some of it is just like offhanded task, offhanded fact recollection. if you had a tool like a web search, for example, then I would expect that the agent performs better on benchmarks like science, reasoning. At least I've read a few data points from this benchmark, so I know the sort of tasks that I did, and some of them to me just appear to be okay. You are recollecting some sort of facts. So again, my guess would be that you would get increase on some benchmarks. Again, it will depend on the sort of tools that you are adding. If the agents cannot use the tool at all, then like the tool is just redundant. So I wouldn't expect any increase in performance at all.
But it's not learning.
Yeah.
It's not really learning to use tools in general. It's using to learn Python.
Right. Exactly. Although again, for this I'm not particularly sure, but I would also expect some generalization of tool use. Probably if like maybe whatever tool that they include, if you also do this non-reason SFT on it, I would expect some form of generalization as well. How much? It's hard to say, basically.
Interesting.
Yeah.
A few different directions
Yeah.
you can continue to explore in this. But
Yes.
their conclusion that they're reaching a plateau.
Yeah. So actually, for one of they actually noted in the paper that they increased the number of like the maximum number of tool calls per trajectory, and like still got the same plateauing or even like downgrading effects. So maybe the type of tool specifically might now like take the agent over the performance bump, but yeah, a direction that's left for exploration, I guess. Yeah.
Good. That was very interesting.
Thank you very much.
Yeah. No more questions for me.
All right.
Well, see you guys next week.
All right.
Thank you, Israel. That was very interesting.
Thank you very much. Thank you for listening and for the questions as well.
And please
Bye.
share
Have
the
a good
link
week.
for the slides.
Yeah.
Please share the link for the slides.
Oh, no problem. I will.
Excellent. Thank you.
All right. Thank you. Yeah. Have a good one.
You too.